Hello everyone again. Today is the starting of a new lecture. The name of the lecture is System of Particles and Rotational Motion. This is one of the most important topics as far as your class 11th is considered, as far as the competitive exams are being considered, as far as your kinematics is considered. Okay. This will involve majority, many topics. We'll go very slowly, understand each of these topics. Rotation, as the name suggests, something is rotating. So we just need to understand the kinematics behind it, analysis, dynamics behind it, and so on. So we'll understand each of these topics. We'll go very slowly. We'll find the analogy between different things, and then move forward. So let us start with lecture number 1. I'm Samir Lawankar. The chapter name is System of Particles and Rotational Motion. Let's begin our discussion. Okay. Let's not look at the course outline right now. We will understand many topics. Let's start with a bit of introduction and then we can move forward with the first concept which you will understand in this chapter, which is center of mass. If you remember correctly, in the lecture Work, Energy and Power also, when we were understanding head-on collision, there also the concept of center of mass came into picture. We will understand clearly what is the center of mass. Let's just first introduce the chapter and then move forward with the analysis. Okay. So first of all, before introducing these complete concepts, there are several assumptions which need to understand, such as rigid body. What is a rigid body? What are the properties of a rigid body, and so on. So let us first understand those assumptions. Let us first introduce this complete topic to you, and then we can move forward with several new everything which you will understand. This will be first time only for you. You will understand several topics, namely called as inertia, radius of gyration, linear momentum converted to angular momentum, torque, etc. So let's not be hesitant regarding any topic. Everything is very easy. Just pay attention to the class. I will help you to make it very smooth and very functioning so that you can understand each and every detail as far as everything is being happening in our surroundings. Okay. So let's start with the introduction of this chapter, which is System of Particles and Rotational Motion. Okay. So in the earlier chapters, we primarily considered the motion of a single particle. So what was happening in those sense? Let us say I take this as a particle and I say that it is moving in this, let's say this direction, with some velocity v. This was basically understood in the chapter motion in a straight line. Okay. Then we increased our dimensions, broadened our dimension. What we said? No, this particle is moving now in this fashion. So what we basically did, we assumed some frame of reference. Let us say this was the frame of reference which we understood. It was X and this was Y. This was understood in the chapter motion in a plane. Fine. So in the earlier chapters, we primarily considered the motion of a single particle. A particle is represented as point mass. So what is the meaning of point mass? Point mass basically means just a single point. So when you put a dot with your pencil or a pen on your pen on the screen, that can be defined as a point. So what does it basically say? That this region, this very, very small region is having that mass m. And that is nothing but the representation or the definition of point mass. Okay. It has practically no size. So you cannot find the size of this. Even the length, breadth, or height of this is 0. Okay. So basically all the concepts which we studied till now regarding the Newton's laws of motion, or let's say motion in a plane, the kinematics equations, all were being applied to motion of a single particle only. So we applied the results of our study even to the motion of bodies of finite size, assuming that the motion of such bodies can be described in terms of motion of a particle. What does this line basically say? So if you remember correctly, generally sometimes I made a block something of this sense. And we said that it is having some velocity, let's say this. Or in the example such as collisions, we made a mass in some sort of this sense. What was happening in very physical, very detailed physics meaning, it was basically a point mass only. Just moving in this direction. In this collision also, there was a point mass only, which was present here and was moving in this direction. Okay, this was the actual physical meaning of point mass. Everything what we understood basically, let us say that this mass was 5 kgs. So we are understanding, or we are making it to be understood in such way that actually the physics was being applied to a point mass which was present at this location, which was having a mass which is equal to 5 kg. You may think that these all things are vague. These all things cannot happen in real sense. How can such a small point have a weight of 5 kg? But these are just the representational way. Actually, what happens will be understood in subsequent slides. Okay. So any real body which we encounter in daily life has a finite size. This is already known to us. Anything. So let us take a very graphical sense, and this, let us say this is that body. In dealing with the motion of extended bodies, now please be clear. You will understand some physics terms here. The first term is here, extended bodies. What is the basic meaning of extended bodies? Extended body basically means that the bodies are having some finite size. Okay. Often the idealized model of a particle is inadequate. Okay, so basically, generally what happens that everything cannot be implemented in terms of this finite mass. We need to understand this body, the finite size, and apply those into our concepts. So in this chapter, we shall try to go beyond this inadequacy. Inadequacy as in, we will move from motion of a single particle to the motion of extended body. So I hope the first concept, that is point mass, is clear to you. And now the second concept, or the future concept which will be implemented, will be based upon the extended bodies, or the bodies of finite size. Okay. So we shall attempt to build an understanding of the motion of extended bodies. What is basically extended bodies? Extended bodies is a system of particles. Okay. So system of particles. So let us take one thing for an example. Let us take this as a mass m. So what we are basically saying? We are saying that it is being comprised of very, very small particles joined in this form, and all of these masses are moving with the velocity with which this is moving. So this is nothing but a system of particles. So we shall begin with the consideration of motion of the system as a whole. The center of mass of a system of particles will be a key concept here. So this is the first concept you will understand in this chapter, that is center of mass. We shall discuss the motion of the center of mass of a system of particles and the usefulness of this concept in understanding the motion of extended bodies. A large class of problems with extended bodies can be solved by considering them to be rigid bodies. A new term came here. The new term is rigid bodies. Okay. Ideally, a rigid body is a body with perfectly definite and unchanging shape. Let us understand this rigid bodies in much more clearer sense. Let us take a very vague number, because we need to generalize every sequence. So that is why I am taking more clearer sense. We will write it as perfectly definite. What does it basically means? That it won't change with time. It won't change with temperature. It won't change with deformation. It won't change with application of forces. I hope it is clear. It won't change with time. It won't change with time. It won't change with temperature. It won't change with deformation. It won't change with what was the thing remembering? Yes, force. So there is no, every time, let's say I apply some temperature, let's say I apply some deformation, let's say I apply some deformation as in some strain is being implemented. Let's say, or some sort of force is only implemented so that it is being tried to be compressed, but there is no deformation happening. Okay. Then some force is happening there. Let's say we apply some force. Then also, if the shape is intact, then such bodies are called as rigid bodies. Okay. The distance between all the pairs of particles of such a body do not change. Let us understand this. So let us say the distance between, let us take two particles here. One particle is P1, one particle is P2, and third particle is, let's say, P3. Okay, so one is P1, one is P2, one is P3. Okay, here the force applied on the, or external force applied on this body is, let's say, 0. Now let me apply some force F external, which is equal to F. So if I apply some force on this body, If this distance r1 and r2 is equal to r1 final and r2 final at any of the phases of application, let's say initial phase or when it was building up to the value of f, at any location, if the values of r1 and r2 is same, then also it is also defined as a rigid body. So I hope you understood the definition of the rigid body, how it is being implemented. Okay. Now let us understand what kind of motion does a rigid body have. Okay. So just give me 1 minute. Yes. Okay. So let us try to explore this question by taking some examples of the motion of rigid body. So till now, what were the things we understood? First of all, we understood a concept which was that we took a point mass concept to understand all the kinematics concept till now. Now we extended it to basically mass of extended bodies. Extended bodies. To understand this concept, what we are basically doing, we are using the concept of center of mass, which will be understood in subsequent slides. Please be patient. Center of mass. Okay, this was first concept. The second concept was based upon understanding rigid body. To understand rigid bodies, we basically understood two different properties of rigid body. The first was about shape. It has a perfectly definite shape which does not change with any properties added or being declined. Properties as in forces, time, temperature, etc. And second thing was based upon your distance between different particles on it. So distance is intact. Okay, so that is how we understood rigid body and point. Fine. Okay. Now let us move forward. So now let us try to explore this question by taking some examples of motion of rigid bodies. So a rectangular block sliding down an inclined plane without any sidewise movement. Okay. So now let us begin to understand this, that a rectangular block is sliding down an inclined plane without any sidewise movement. What does it mean? So basically let us take, let me make a 3D figure for this. Let us take this as to be that body, rectangular block, and it is being said that there is no sidewise movement. That means it is not moving in this direction, it is not moving in this direction. So I hope that concept is clear. Okay. So now the block is a rigid body. So its motion down the plane is such that all the particles of the body are moving together. Okay. So please understand this very clearly. As it is rigid body, what it basically means? It simply means that, let us suppose, let me make it as a bigger point. Okay. So the box was some sort of this. Let us take this to be some value which is P2, and let us take this to be some value which is P1. Okay. So at some time t is equal to 0, the distance between both of them will be a displacement vector, let's say known by r. Let us say at some time t is equal to t1, this box reached this location. This location as in it was its initial location here, and let us say this was the final location here. So then also the distance between both of this is same. Then only we can say that the motion of a rigid body is being implemented. Okay, so the block is a rigid body. Its motion down the plane is such that all the particles of the body are moving together. That is, they have the same velocities at any instant of time. So let me just write this line here. So basically what I'm saying is that the motion of the body down the plane, is such that all the particles as in all the particles which are being present here. Okay. So only two examples have been explained, but it can be explained about all the particles here, such that all the particles are moving together. Okay. So if you can see clearly that if all the particles are moving together, that means their velocities is also same. right? Because the amount of displacement each of these particles are having will be same in that time delta t. So we can also say also the velocities are same. They have same velocity. They means as in all the particles. Okay, all the particles have same velocities. So when such thing happens, please attend, listen to this carefully. So when such thing happens, then the rigid body is said to be in a pure translation motion. So when such thing happens, then it is said to be, then the body is said to be in pure translation motion. Okay, so I will write this again. So what happens in pure translation motion? So in pure translation motion, all particles of the body, all particles of the body have the same velocity, have the same velocity at any instant of time. At any instant of time. Okay, so I hope this line is clear to you. So just iterating again. So in pure translation motion, all particles of the body have the same velocity. They have the same velocity at any instant of time. So this is basically the definition of your pure translation motion. Fine. So I hope pure translation motion is clear to you for the rigid body. Now let us understand something more unique. Okay. So now what is happening here? Here you can see a cylinder, basically a cylinder. It can be metallic or a wooden cylinder, which is now going down the same plane. Please refer to my words very clearly. I said going down the same plane. In more physics terms, I can say the cylinder is rolling down the incline, and that is why the word uses rolling. So it is called as rolling motion. We will also understand about rolling motion in more detail at the end of this chapter. But usage of words here is very, very important because every word has different meaning here. Rolling, rotation, translation plus rotation, all of these are different meanings. We will understand each of this very clearly. Let's first understand what is happening. So here we understood about translation motion. Now let us understand what is the motion being happening here for this or what is being happening here for the solid metallic or wooden cylinder down the same incline. Okay, so here the rigid body shifts from the top of the top of the inclined plane towards the bottom. So you can see as the, let us look at this clearly. So here this value of P2 and this value of P1, okay, the distance between them will always be same. The distance between them will always be same. But if you see clearly, this will keep on rotating. The distance will be same, but it will keep on rotating. The value of P1 will be same. P1 will be at this location only. So if you see clearly, P1 will move in this direction only. But what will be the P2? P2 will move in some sort of a spirally fashion like this. So I hope you can understand some sort of how is the motion of P2 happening. Okay. So consider here the motion of a solid metallic or wooden cylinder down the same inclined plane. The rigid body in the problem, which is the cylinder here, shifts from the top to the bottom of the inclined plane and thus has a translation motion. So because this complete system of particles is going from this top position to this bottom position, then that means it is sure that it is translation motion. Okay, but as you can see here, all of its particles are not moving with the same velocity. Why it is being written like this? Let us understand. So if you see clearly that velocity at this location is in this direction here. If you remember the concept of uniform circular motion, we know that velocity is nothing but equal to r omega, correct? So if I change this value of r, this value of velocity will change. That means as I go on away from this value of center, my velocities will change. And that is why what we can say that all particles, let me write that line here. So all particles here are not moving with the same velocity with the same velocity at an instant. Therefore, what we can say that it is not pure translation, right? Therefore, this is not the case of pure translation. Okay, so therefore this is not the case of complete pure translation. Something more along with translation is happening here. Okay, so that something more is nothing but your rotation. Okay, that's something new is rotation. We will understand about rotation. This complete chapter is rotation only. So don't be hesitant. Let us understand more about this. Okay. So in order to understand what this rotation is, first of all, let us take a rigid body and then constrain it. And it constrain it so that it cannot have a translation motion. Okay. So I think that explanation is given here. Huh. So let us first understand something regarding this concept here. Okay. So let us first understand pure rotation so that we can understand translation motion plus rotation. Okay. So let us first look at this location here. So see clearly what is happening. Okay. So in order to understand what is this rotation, let us first take a rigid body. So let us take this fan as a rigid body here. So this is a rigid body. Okay. And let us constrain its motion so that it cannot have a translation motion. So you know the direction. What is the direction? So basically it is rotating like this, correct? So hence here no translation motion occurs. So here no translation motion occurs because why? Because we have constrained the rigid body. So this is the constraint being offered to the rigid body. Okay. So now what can happen? So now what can happen? It can only rotate in this fashion. Correct? Fine. So the most common way to constrain a rigid body is so that it does not have a translation motion is to fix it along a straight line. So you can see clearly that what we have just imparted a axis of rotation to it, or basically we have fixed it along the straight line. Similarly, you can see this also. Here also we have done the fixity along the straight line so that the rigid body is now constrained from its translation motion. Fine. So let me just write it here. So constraining of rigid body is done so that constraint of rigid body is done so that no translation motion can occur. Okay. So now we can define what is basically rotation and what is basically axis of rotation. Okay. So now this motion of body is basically this rotatory motion. This rotatory motion of body is called as rotation. Okay, so this is how can you approach to this location when we have constrained the rigid body. This is very important. So when we have constrained the rigid body, then and only then we can observe a complete rotation of the object, of the body. Okay, and also the line along which the body is fixed, the line along which the body is fixed is termed as axis of rotation. What it is termed as? It is termed as axis of rotation. Okay, so I hope you understood this concept. What is your axis of rotation and what is basically rotation? Okay, so let's look at this diagram first of all, just to look at some of the examples. So if you see clearly here, it was being fixed at this location, right? This is nothing but its axis of rotation, right? And this is how the motion is being occurred. Similar to this also, here the axis of rotation is basically this. This is your axis of rotation, and this is the movement which is happening, which is rotation. Here also you can see for the skater, this is the vertical axis on which she is rotating like this. So she is also in pure rotation. In the case of Earth also, at this is your axis of rotation through which the rotation of the Earth is happening. Okay. Similarly, for this log also, this log of wood also, this is the horizontal axis through which there is a rotation happening. So these are all the examples of pure rotation happening. Okay. So the line along which the body is fixed is termed as your axis of rotation. And these are all the examples which we can understand regarding pure rotation. Okay. So now let us understand more about rotation now. So we notice here that in rotation of rigid body about a fixed axis, every particle of the body moves in a circle which lies in a plane perpendicular to the axis and has its center on the axis. So let me explain what I just said. So if you see here clearly, just see this diagram clearly. First of all, let me explain the diagram and then we can move forward. So what happens in actually, so this is an example of pure rotation only. Okay, so in pure rotation, let us assume that this is your axis of rotation. So if this is your axis of rotation, okay, let us assume that there was some particle P1. This was that particle P1 which was rotating. Now if this complete rigid body is rotating like this, then what will be the movement of this particle P1? It will be rotating some sort of in this fashion. If you see this diagram very clearly, you can observe that it is only and only rotating in a plane. Correct? And that is the plane which is given here. So this is the plane here, right? So let me first write and then I can explain it again. Let me write it here only. Okay. So in rotation of a rigid body, about a fixed axis, every particle, so particle as in P1, P2, P3, I just explained. Every particle of the body moves in a circle, which lies in a plane perpendicular to the axis and has its center on the axis. Okay. So what I just wrote that in rotation of a rigid body about the axis, all these particles which are being implemented here are always lying in the plane, or basically they are moving in a circle, and that circle lies in a plane perpendicular to the axis. So let us just go here. So it is all lying in a circle, and this circle is basically perpendicular. So basically this is 90 degrees. This is also 90 degrees. So it is perpendicular, lies in a plane which is perpendicular to the axis and has its center on the axis. So the circle center is on the axis. Fine. So I hope this is clear to you. Let's move forward. So now let us look at this. So this diagram has been explained, whatever was happening here. So let us look at the particle P1. So what is happening for P1? So P1 is basically rotating in this circle with the center which is C1, correct? Similarly, C2 or basically the particle P2 is rotating in this circle with radius R2. If you need to find the same for this particle P3, you can clearly see that it is also rotating. Sorry, it is not rotating. Why? Because the radius is 0. Right, so the particles which are on the axis, I may just write this line also here. So the particles on the axis of rotation, do not rotate as r is equal to 0. Okay, so I hope this concept is also clear to you. So any such particle remains stationary while the body rotates. Okay, so any such particle remains stationary while the body rotates. So this is expected when? This is only and only expected when this axis is fixed. So possible when this axis is fixed. It is written here also, this is expected only when the axis is fixed. Okay, now in some examples of rotation, however, sorry, so in some examples of rotation, however, this axis may not be fixed. Let us understand that examples also. So just quickly look at this top which has been rotating. Okay, so it is quite evident. First of all, let us understand each and every concept. We started with something called as translation motion. Just look at this diagram and see that is there any translation motion happening? The answer should come out to be no. Why? Because as you can see that these particles are not moving in, let's say, this direction, or let's say this direction, or let's say this direction. Right? They're only rotating. So if I let us take which particle should I take? So if you see clearly that the axis of rotation is itself not, so basically it doesn't have some axis of rotation here. There is only a point through which the rotation is happening. So that is the basic sense which we need to understand, which I need to make you understand in this concept here. Here basically the axis may not be fixed. The axis of such a spinning top moves around the vertical. So you can see that at some instant the top was in this way. In some sense, the tabletop is in this way, right? So if you see it as a completely working phenomena, you can see that the axis of rotation is basically making a circle, or basically making a cone, not even a circle. It is making a cone like this. Okay, so that cannot be understood as something called as a fixed value of axis, right? So the axis of such a spinning top moves around the vertical through its point of contact with the ground, sweeping out as a cone. So we understood how this thing came. Okay, so basically even if you see, just use a top, so you will find that the motion or the axis of rotation is basically in this way. Some say here, then there, here, then here, then here, then here, then here. So if you join this all, you will get a cone. This movement or axis of the top around the vertical is termed as precession. So it's just for reference purposes. Let us understand one more. So if you see an oscillating fan, so these are generally in all the homes. So there is a button. There's a button here, so that you can utilize the motion in this way. Let's say it's a sway motion. So let's say it's moving this way, that is going this way. Similarly, there's another button through which we can refer to the height of angle of inclination of this fan. So we can make it in, let's say, this fashion, or we can even make it in this fashion. Okay. So how can we understand this thing? So here clearly the rotation angle is not a single axis. It's a simple point, which is the concept which you need to understand. So in the previous case, it was a cone. This time it is basically a point. So this is a second example, but just to make things simpler case, just to not add all the complexities rightwards, in our study, however, we mostly deal with simpler and special case of rotation in which one line is fixed. So we will only take case into scenario in which we will take the rotation along the axis of rotation, which is always fixed. Thus, for us, rotation will be fixed about a fixed axis. Thus, the rotation will be about a fixed axis, only otherwise stated. Okay, stated otherwise. So basically, only the applications or just the information is being put. It is not always a criteria in which you will get your axis of rotation as a fixed value. It also can be a cone. It also can be a point. Okay, so those examples are also being put up here. Now let us go back and understand this concept again. So here, first of all, what you need to understand that something. So this is basically a translation motion. This is basically a case of translation motion plus your rotation. Okay, so this is an example of a translation motion and your rotation. Okay, so what is the final observation here? So final observation is basically, first of all, so in the present chapter, we will consider only rotation motion about a fixed axis, right? And complete conclusion till this was, first of all, we understood about the translation motion. And second thing we understood about pure rotation. So we understood about pure translation. We understood about pure rotation. And then we also understood something which is translation plus rotation. So that thing being said, that was a simple introduction of the complete chapter which we are going to understand. So basically, what is the final conclusion of this complete discussion was that in the complete analogy which we will be understanding, we will always take the rotation to be along a fixed axis, first thing. And second thing is that we will always understand this complete concept as either a pure translation motion or a pure rotation motion or translation motion plus rotation motion. Okay. So with all that discussion happening, let us start with the first concept to be studied in this complete chapter, which is center of mass. Okay, so let me introduce you to center of mass directly. So we shall first see what the center of mass of a system of particles is and then discuss its significance. So let us first understand what is this, how to calculate the center of mass, and then understand how we implement it. So what was the basic reason of understanding the center of mass? Okay, so we will understand the significance afterwards. Let's first understand what is this center of mass. Okay, so let us understand. So just look at this diagram very clearly. So what is the diagram shown here? It's an XY axis. The mass m1 is kept here, the mass m2 is kept here. Okay, so seen clearly, it is nothing but a point mass. So this is also a particle point mass and this is also a particle point mass. And the question depicts that you need to calculate the center of mass of the system of particles. What is the question? Question is find, every word is important, that's why I'm writing. So find the center of mass of system of particles. Find the center of mass of the system of particles. Fine. So we shall take so for more conceptual clarity, we took both the masses on the x-axis only. Okay. Let us take this to be the origin, right? So center of mass is basically a distance only. So we will find calculate that distance from this origin O. Let us assume that the mass m1 is at a distance which is x1. Let us assume the mass m2 is at a distance x2. Alright, so the distances of the two particles be x1 and x2 respectively from some origin O, and let m1 and m2 be the respectively the masses of the two particles. Okay, clear. Okay, so now what is the center of mass here? So let me first write. So the center of mass of the system, is the point C. This is the point C being explained here, right? Given by, please understand this. So basically the distance which is capital X is nothing but equal to m1 x1 plus m2 x2 upon m1 plus m2. Okay, quite clear understanding is being done, right? So here this X can also be regarded as weighted average mean or weighted mass mean. So mass weighted mean. Why mass weighted mean? Because mass is used as a weight here to understand the weight is basically that weight which we understand in the concept of statistics. Okay, so it's a mass weighted mean of the particles, or basically x1 and x2, or the distances basically x1 and x2. Okay, let us take special case here. If masses are same, that is if m1 is equal to m2 is equal to m, then capital X is nothing but equal to x1 plus x2 by 2. Okay, so I hope this is clear to you. Thus, for the two particles of equal mass, the center of mass lies where? It lies exactly at the midpoint. So midpoint of two masses. Okay, so that thing being explained. Now let us generalize the statement here. So let me generalize the statement here. So let us take that there are n particles. Okay, so if for center of mass of n particles having masses m1, m2 dot till mn along a straight line kept at a distance kept at a distance x1, x2, dot till xn from the origin O, from the origin O is equal to what? It is basically equal to x. This is equal to, quite clear, it's m1 x1 plus m2 x2 plus dot mn xn upon m1 plus m2 plus dot till mn. So I hope this is clear. Now similarly, from the concept of statistics, we have understood a significant symbol which is called as summation. So summation is basically equal to, so it can be also written as summation mixi upon summation m. So this is basically the center of mass of n particles when we are only considering along a single dimension. Okay, fine. So that thing being said, let's move forward. Okay, let's understand more about this. Okay, so here, what was the final configuration? What was the final understanding we got? We got that center of mass is x, which is equal to summation mixi upon summation mi. So here, see clearly, summation mi can be written as equal to capital M. The complete sum of the body, let us take this for the complete n particles, which is let's say we are talking about a body. If that body is having system of n particles and the masses summation of all those particles will be equal to m, capital M basically. So this m is basically total mass of the system. In this case also, we can take this complete, let us take, I make different scenarios here. So the mass m will be nothing but summation of all these particles. It's total mass of the system. Okay, so that thing being said, so this was being done for one dimension, correct? So these concepts were being explained for a single dimension. Now let us generalize the statement and let us understand the center of mass of the system of three particles along a coordinate. Okay, so how to convey this? First of all, let's go with two dimension only. So if I explain you for two dimensions, let us assume this to be your x and y axis. So this is your x axis, this is your y axis. Let us take this to be some m1 value, this is to be some m2 value, this is to be some m3 value, this is to be some m4 value, right? So if we drop the components from this location, we can directly find out the values of x1, y1, x4, y4, x2, y2, x3, y3. Okay. Therefore, from the similar fashion, what we can say directly, and what is the center of mass? The center of mass can be written as capital X, which is nothing but equal to summation mixi upon summation mi, also equal to summation mixi upon capital M, and capital Y can be written as equal to summation miyi upon summation mi, which can be written as equal to summation miyi upon summation m. Okay, so I hope it is clear to you how we got these results. Okay, so let me stop it here only. We will understand the three-dimensional part of calculating the center of mass and the vector part, or how we can represent this complete discussion in terms of vector in the next class. Okay, let me stop it here. So currently we have completed with the introduction of this complete chapter in which we understood about pure translation motion, pure rotation motion, axis of rotation, and translation motion plus rotation happening. And we started the discussion of center of mass. We understood the basic analogy of center of mass of single dimension, also the formula for the two dimension. We'll move further with it and then understand it for three dimension. Okay, so let me stop this lecture here only. Thank you so much.